it's like, so my Tuesdays and Thursdays are long, and then the Wednesdays are shorter, but I'm usually tired on the Wednesday because of the Tuesday and the Thursday. So let's have a look. So we're going to do Faraday's Law. It's the third chapter in our bit on magnetism. And we're going to talk about Faraday's Law, which is all about changing magnetic flux and its effect on electrical signals, electrical voltages and currents down a wire. And then we're going to talk about a thing called motional EMF. That is the EMF caused by the motion of, say, a conductor through a magnetic field. And then we're going to talk about Lenz's law. And Lenz's law basically says that the system tries to stop me from changing it. If I try to create a current, it tries to stop me from creating a current. If I try and stop a current, it tries to stop me from stopping a current. It's a very conservative thing. And so those are the three main things. And we'll talk about the generalized form of Faraday's law, and we'll talk about Maxwell's equations. And I've said in the past, I don't do much with these two. You're going to get Maxwell's equations if you do EE later on. And you're going to live and breathe them for a while. I think I've got enough on my plate to get you to the stage where you've seen them and, etc. This is quite conceptual, which is good and bad, This is a little bit non-intuitive. Let's start with Faraday's law. So let's imagine we have a loop of wire and we have some kind of current detection device, and we're going to call it a moving coil galvanometer or center zero galvanometer, because galvanometer means it's really sensitive current meter, and the center zero means if the current flows one way, the needle goes to the right, and if it flows the other way, the needle goes to the left. We used one of these when we were doing the electric field plotting. Single loop. Magnet, strong magnet in my hand, not a weak magnet. And if I just lay the magnet next to the loop, I see absolutely nothing. I only see a current flow when the magnet moves. It's a bit like the charge only feels the force when it moves in a magnetic field. I only get current flow in this loop of wire, the one that goes through the meter. I only get current flow when the magnet is moving. If I make the magnet stronger and move it, I'll get a bigger deflection because I've got a stronger magnet moving backwards and forwards. If I move the magnet faster, I get a bigger effect. If I move the coil and leave the magnet alone, I can get this effect. So it's not about the motion of the magnet per se, it's about the motion of the magnet relative to the coil, relative to this loop of wire. If I was to turn the magnet around so that rather than moving a north pole towards the coil, I move the south pole towards the coil, I would get the opposite effect. So if it deflected to the right for the north, it would deflect to the south, to the left for the south. If I send a magnet north pole in and it goes to the right, when I pull the north pole out, it goes to the left. So this is a weird interaction where the size of the interaction depends upon the strength of my magnetic field, depends upon the speed of the change, and there's a polarity kind of thing involved. But the bottom line is I can take mechanical energy and I can create electrical energy. And that's a generator. Before we did the motor, now we got a generator. Not a very good one, but it's a generator. And if you basically used one of those emergency lamps where you squeeze the trigger a whole bunch of time and the light comes on whenever you're pedaling the trigger, it lights, or one of those radios where you wind it up. They're all changing mechanical energy into electrical energy. Yeah. So with a bicycle, what they do is they have an axis that's driven by the wheel, which then turns one of these, which gives you electricity. Yeah, dynamo effect. Yeah, cool. But I thought we'd learned that we could switch out an electromagnet, a bar magnet for an electromagnet. It wasn't, bar magnet, 18th century stuff, and now we have electromagnets and all that kind of stuff. And that's true. We tend to use electromagnets whenever we can. Although there is utility for a bar magnet that goes beyond having the little sticker that goes onto your refrigerator. Have you noticed that with new refrigerators it doesn't work? They have plastic fronts, they don't have metal fronts. So you put your little sticker, the whole industry is going to kind of like go out, and it's like, next they'll send you an attachment that fixes onto your plastic refrigerator front to make it magnetic so you can stick them back on. But they do use permanent magnets in motors sometimes. They use them when they need to, But often if you want control and you want to be able to turn the system off, etc., use an electromagnet. So here's an electromagnet. Now this is from the old book, and they switched the diagrams around so that now the magnetic, the producing effect is on the left, and the receiving effect is on the right. So, but the idea is, if I simply take a coil of wire, like a solenoid, and I energize it, that's increasing the magnetic field, which is like bringing the magnet closer. And if I open the switch, that's reducing the magnetic field, which is like pulling the magnet away. So I can get this backwards, forwards effect using electromagnet. The ring is there. When the problem with all magnetic fields is they tend to basically, diverge from the ends of them, and that's a bit of a problem. So if I'm trying to get a magnet to talk to a loop, the problem is that it tends to diverge away from it. But if I can entrain that magnetic flux, remember the flux is the number of arrows. That's what I think of as flux. Flux is like the number of arrows that I imagine. If I can entrain that flux so that it doesn't spread out, I can keep a strong magnetic field. And it turns out that iron is great for that. Soft iron is great for that. So they tend to put coils around soft iron. And the magnetic field lines, rather than leaving, go through the next thing in line, so they kind of go down here. So we get a stronger effect. Soft iron yoke, they sometimes call it. Yoke, like yolk of an egg, or really it's like the yoke that was on a donkey to do some pulling, that kind of yoke. That's why transformers tend to be really heavy. If you pick up some of the old power supplies in the lab, they take AC and they use a transformer to bring down its voltage, increase its current, and then they rectify it to give it DC. And basically when you pick those things up, they're really heavy because they've got a big iron transformer in there. Okay, so we don't have to have a magnet physically moving backwards and forwards. We can have to do something similar with a circuit. Make an electromagnet. We're going to find out in a little bit that make an electromagnet, sometimes we do it on purpose, and sometimes inadvertently we've made a little bit of an electromagnet. Just because we have current flowing in a loop causes a magnetic field. That's what Boyer-Savart tells us. And sometimes we create a magnetic field and we don't really want to, and we've got to live with the consequences of it. And we'll get to that. So along comes Faraday. Faraday basically says what he notices that the EMF, that's the voltage source, the EMF that is induced in a circuit is directly proportional to the time rate of change of magnetic flux through the circuit. So I'm taking this coil and I'm moving it backwards and forwards, and I am creating a current, and that current, basically you can imagine it as arising from an EMF. So it's as if I put a little battery in here. How big would that battery be? That battery would be equal to minus the rate of change of flux with respect to time. Okay. Supposing I had more than one turn. Supposing I had a coil rather than a loop. It does multiply. So if I have 10 turns, I get 10 times the effect. If I have 20 turns, I get 20 times the effect. Because each turn is affected by a certain amount. So if I have more turns, I get more effect. Let's do a couple of these. A wire coil consists of 20 turns. So let's do that. I like to, just my shorthand, I show a coil like that. It's basically like a ring with some width to it. N is equal to 20 turns. Electromagnet, the magnetic flux through the coil changes at a uniform rate from 8 Tesla meter square to 12 Tesla meter square in 4 seconds. So I'm going to show this is my flux. I don't have to show all the little lines, I just have to show, you know, there's my flux. And flux initial is equal to 8 Tesla meter squared. And flux final is equal to 12 Tesla meter squared. And my delta T equals 4 seconds. If you want, you know, you can, I mean, especially when you first begin, visualization is important. So this is flux initial, this is flux final. How did this happen? I don't know, I don't particularly care. It just happened. You know, we've got this change in flux. What is the magnitude of the EMF induced in the coil? So I can imagine an EMF, you know, like what would be there or there? It's going to be as this change occurs. And I say my EMF is equal to, what did we say? Minus N d phi by dt. If everything's changing nice and steadily, I can say that's delta phi by delta t, if it's changing nice and steadily. So my EMF equals minus N phi final minus phi initial over T final minus T initial minus 20. What did we say? 12 minus 8 over 4, which equals minus 20 4 over 4 minus 20 volts. So my EMF equals minus 20 volts. Sine, don't worry about the sign for a minute. We'll use that sign later. Okay. So if I change my magnetic flux going through a loop or a coil, I will get current flowing around that loop or that coil, and it will, you know, currents are associated with driving forces, EMFs, and so it's as if I put a battery in there. I didn't, but it's as if I put the battery in there. How many of you have ever used a not a rechargeable, but one of those one of those toothbrushes that you just sit on the stand and is electric, but you just sit on the stand. There's no wire connected to it. There's a little stand that has a wire connected to it, but the toothbrush itself does not have a wire connected to it. That's making use of this technology. It's induction, basically. You can link things via a magnetic linkage as opposed to electrical linkage. I can create an electric potential which causes electric current in a loop of wire because I change the magnetic field that loop of wire sits in. Yeah.
Starting with the countertops that you could put cell phones on.
Yes, that's exactly right. Yes. So I'll tell you a funny story. Hold on, let me just stop this for a minute, because. Okay, so. All right, so when we get a change of flux through a loop, we get this effect. We can cause this effect. So what we say is, we say E is equal to, where's my pen gone? We say E is equal to minus d phi b by dt. And then we remember good old Gauss's law that flux was equal to the integral of B dotted with a little bit of area. And we could write that in the magnitude form by saying it's the magnitude of B times the magnitude of A times the cosine of the angle between, because it's a dot product. And so that tells, well, hold on, if I want to change my flux, maybe I can change my B, or maybe I can change my A, or maybe I can change my angle between my B and my A. And that constitutes a change in flux. So I can substitute and I can say my EMF is equal to minus d by dt of BA cosine theta, and I can change any one of these or all of them that I want. So I can imagine, I could, for instance, I could make the magnetic field stronger or weaker. I could somehow change the area of this loop. Or I could somehow change the angle between the B and the A. So there's my A angle, there's my B. So I can change this angle by maybe spinning the coil. And that's actually what we find most convenient to do, actually, is just spin the coil. A coil of wire consists of 40 turns. So here's my coil of wire. N is equal to 40 turns. The magnetic flux through the coil changes. So first of all, what is the magnetic? I've done this question before, so let's change it a little bit. Let's say the magnetic field. Let's do the field this time. The magnetic field through the coil changes a uniform rate from 2 Tesla to 9 Tesla in 4 seconds. The area is 4 square meters and B is perpendicular to A. So I'm adding a few things in here. I got to tell you the angle. So there's my B. Oh, sorry, no. It's parallel to A. And there's my A. Yeah. I got to give you the angle. So what I say is, well, my EMF is equal to minus d phi by dt. And I know that my flux is equal to BA cosine phi. So my E is equal to minus d by dt of BA cosine that. So my that is equal to, well, if it's nice and steady, I can have minus delta. Well, let's save that for one step. Let's take out everything that's constant. So let's have a look. My B's constant. No, my B is not constant. So it's going to be A cosine phi dB by dt minus. So my flux is my EMF is equal to minus A cosine phi delta B by delta T, which equals minus A cosine phi B final minus B initial over delta T. So this equals minus, and my A I said was 4 meters, and it's cosine of 0. Yeah, because I said they were parallel. B final is 9 Tesla, B initial is 2 Tesla over and 14 seconds. So this is going to be, did I bring a calculator with me? Yes. So then we have 4 times cosine of 0 is 1. So 4 times 9 minus 2 is 7 divided by 14. Oh, I could have done that in my head actually. So that's going to be minus 2.
So do not multiply by the turn.
Multiply it by the current.
Turns. Number of turns.
Well spotted. It's a good idea to learn these things with that already in, then you won't make that mistake. E is equal to times 40. And I would take points off in the test if you didn't put that down. So just, you know, don't give me the points. Yeah, cool. So I can change B. This one I have turns. I have a magnetic field. I'm changing the area. So I have, and somehow, you know, how do you change the area? Let's not worry about that. But sometimes I can show you a way you can do it. It's not as elegant, but I can show you a way you can do it. So I say, well, let's have a look. I know my N equals 10 turns, and I know my B is equal to 12 Tesla. That's a constant. The area initial equals 3 meters squared. The area final is equal to 7 meters squared. My T, delta T, in 5 seconds means delta T is equal to 5 seconds. Not by 5 seconds, but in 5 seconds. My EMF is equal to minus N d phi by dt. So, and my phi is equal to BA cosine the angle between. So my E is equal to minus N d over dt of BA cosine the angle between. Let's take out all the stuff that's constant. Well, my N is constant, and this time my B is constant, and my cosine the angle is constant, but I have a dA by dt. So then I say, well, my E is equal to minus, let's put numbers in, minus 10. My B is 12. Cosine, do I give you the angle? What is the EMF induced? Call area changes. You know, bad question. I should say that B is parallel to A. I'll give you some angle. B is at 30 degrees to A, something like that. So this is going to be the cosine of 0. And then I have A final. So I have my A final, which is 7 minus 3 over 5. Cosine of 0 is 1, so that's going to be 5, oh no, 4 over 5. Bad luck. that would be 5, that goes 10, that goes twice, that's 24. 24 times 4 is going to be 76, I think. Let's have a look. 10 times 12 times 4, enter, divided by 5, 96. Did I do that right? I think I did that right. 24 times 8, 12 to 96. Yeah, that's right. Cool.
Actually, what was the area for the last problem? The area in the theta?
I said the area was 4 meters squared.
Okay.
Yeah, I had to write that in. Third one. A coil of wire consists of 15 turns. This is N equals 15 turns. The strength of magnetic field that passes through the coil is 12 Tesla. The area equals 3 square meters. The angle between the magnetic field vector and the area vector changes. So let's do it like this. Let's do and that's 25 degrees, and that's 70 degrees. So I'm looking down from above. In that second diagram, I'm looking down from above, yeah? And I just twist the coil. And I say my EMF is equal to minus N d phi by dt. And my flux is equal to BA cosine the angle between. So my EMF equals minus N d by dt of BA cosine theta. Now let's take out everything that's constant. So I have minus N, B is constant, A is constant. I have d cosine theta by dt. So my E is equal to minus 15 times 12 times 3 times delta. So let's put it down as cos theta final minus cos theta initial over delta t. So my EMF equals minus 15, 12, 3, cos 70 minus cos 25 over four seconds. So E is equal to, now I've got to be a little bit careful here. I'm going to do the cosine bits first. So it's going to be cosine 70 enter minus cosine 25 enter. I'm going to do that again, bracket. Cosine 70 close bracket minus cosine 25 bracket enter. Okay. Times 3 enter times 4. I'm sorry. Times 12 enter times 15 enter divided by 4 enter. And I'm getting minus 76.2 volts on that. Let me just double check that a bit. So cosine 70 is 0.3, and they're going to subtract from that cosine 25, enter, yeah, minus 0.05, and then multiplied by the rest, yeah. Most common mistake on that is people will take the two angles away from each other and say the cosine of 70 minus 25 is the cosine of 45. And it's not, of course. It's the cosine minus the cosine, not the cosine of the difference in the angle. It's not the same thing. So, so watch out for that. So three possibilities. You change the flux, well, four really. You change the flux, you change the magnetic field, you change the area, you change the angle. So 4 possibilities based on 2 equations. I won't change more than one thing at once. Okay. Next, motional EMF. So this is actually it looks like we're going in a different track, but we're just doing a little sidestep, and then we're going to go back, continue what we're talking about. So imagine you're an aeroplane flying through the Earth's magnetic field. What you would find over a period of time is that you would tend to build up a charge across your wings, and that charge build-up would depend upon your speed and the strength of the magnetic field and all that kind of stuff. You'd reach a balance, of course, because as you put more positives at one end and more negatives at the other, you're building up an electric field. The electric field wants these things to combine, your magnetic field wants to separate these things. At some point there's an equilibrium where the strength of the combination force is equal to the strength of the separation force, and that's the equilibrium position. What we say is consider a metal rod that travels through a uniform magnetic field. It's full of free charge carriers. It's metal, so it's got free charge carriers in, and we're moving them very fast. Not as fast as the electrons in the electron beam that we did on the fine beam tube, but they're moving fast. And so they're going to feel a force. And we did that before. We said F equals QV cross B. Yeah. So we say the motion causes charge separation, so charges build up at the ends of the metal rod. This creates a potential difference between the ends of the metal rod. And we say, well, from a magnetic point of view, we have QV cross B. And from an electric point of view, we have Q times E. And this is the electrostatic force, and this is the magnetic force on a charge carrier. And so we end up with an equilibrium where the two things are balanced. And we can say, well, the Q's go away, and we say our electric field is equal to V cross B. Now, if we remember that change in electrical potential equals the electric field times my length. Let's just go back to our little square, and we had force, and then we had electric field. If we multiplied force by a distance, we got delta U. If we divided that, we got delta V. So what we're saying is if we want to go from force to delta U, we multiply by the distance. And if we want to go from electric field to electric potential, we multiply by distance. So if I get E and I multiply it by a distance, I get change in potential. And my change in potential would be V cross B, that's my E is equal to V cross B from above, times L. And so I get BLV. And I think I want to start writing that down as that's going to be, what's it going to be? It's going to be LV cross B. So what I noticed, just what I just spotted in the last test is we had a whole bunch of stuff about delta U is equal to Q V cross B, and people weren't or alternatively, people weren't remembering the cross product. They were kind of just, you know. So I want to be a bit careful. This is at 90 degrees, so we can just write it down as the, you know, the powers. But we shouldn't really do that. So I got to be a bit careful. I'm going to go through my notes to be a bit more careful. I'd like you to be a bit more careful about stuff like this. Is easy to remember, but it's sometimes just an oversimplification of what we need. You know. Okay. So a 3 meter long rod of metal moves in a uniform 20 Tesla magnetic field at 8 meters per second. The rod length is parallel to the x-axis. So there's my rod's length. This is 3 meters. And the magnetic field is parallel to the y-axis. So my B, I only draw one of them, but remember that, you know, I could draw a whole bunch of them through this diagram because there's a whole bunch of them and they're parallel. And the rod's velocity is parallel to the z-axis. So here's my velocity coming out there. What is the EMF induced in the rod? So what was it? It was V L cross B, was it? Let's go back. It was L V cross B, sorry. So it's delta L V cross B. So E is equal to 3. And let's just do one more step. So E is equal to delta L V B. It's a cross product sine of the angle between, which in this case is 90, which is 1. Okay. So then we say, well, okay, E is equal to delta L, which is 3, times V, and our V is 8 meters per second. And then B is 20 Tesla times 1. So E is equal to, there should be a, well, that's going to be 160 times 3 is 300, 480. 480 volts. Cool. So that's what we get at equilibrium, 480 volts between those two. At 20 Tesla is an amazingly strong magnetic field. I mean, you know, it's a ridiculous amount of strength on the magnetic field. Cool. So now I got, let me have a look at my timer. Yeah, I've got a little bit of time. Let's have a quick look ahead and look for a place to, yeah, okay. I'll do this slide and then we'll take a break. So, okay. This is how we can change our area. We have a rod that rolls on some rails. If it rolls to the right, the area is bigger. If it rolls to the left, the area is smaller. So my loop is basically that rail down to there, up through there. That's the size of my loop. But I can make it smaller by moving this rail, moving this roller one way or moving the roller the other way. Okay? So it's a way of changing my area of my coil. Remember, there were 3 ways. I could change the magnetic field strength, I could change the area, or I could change the angle in time. Those are the things. This is the way I can change the area. Okay. So I need to basically be able to visualize the flux going through this. So I'm doing these little X's I prefer them with circles around, but the book tends to not worry so much about that. But I've got all this pattern of little X's inside. I'm going to spend some time drawing them, but that means my magnetic field is going into the board, not only on the inside, but also on the outside. It's not just, it's just the magnetic field that this thing is bathed in goes into the page in this region. It's just the way it is, etc. We say consider a circuit that has a moving section, a sliding rod. The area of magnetic field enclosed by the loop can change by moving this thing backwards and forwards. This induces an EMF that acts like a cell. So the flux. So I've got an EMF that is caused by, what was it? It was caused by minus N B A cosine theta, yeah? And then I have another EMF which is caused by minus L, what was it? V cross B, yeah, that's right. B comes at the end, yeah. Okay? So, okay, they're equal to each other. They're going to be equal to each other. Now, if they're at 90 degrees to each other, then I don't need to worry about that angle, and I don't need to worry about the angle of that. That can be down as minus L V B. So there I have B. So stuff starts cancelling. So I say my magnetic flux is equal to B times L times X. So L is the length of my rod, and X is that distance there. So that's the area. So my flux is equal to the magnetic field times the perpendicular area. So that makes sense. And then I can use Faraday's law. E is equal to minus d phi b by dt, which equals minus d by dt of phi b will equal BLX. So I get E is equal to minus B and L, because they're constants for this example, dx by dt, which is velocity, minus BLV. So, oh, hold on, minus BLV. So basically, whether I go using one route or go using the other route, I end up at the same answer. Okay? And I've not got an example of that, so let's take a break. Let's do a 5-minute break, and then I'll see if I can find something. Hold on. So let's go to stop.